Recall the legendary Young's double-slit experiment. This experiment was meant to demonstrate the wave-particle duality of particles. And essentially it shows that a photon behaves in a strange, incomprehensible way if we detect it. This effect itself seems astonishing. It invites a certain mystification of the theory, and it creates the impression that any scientific rigor, as they say, has left the chat. And the thing is, this effect doesn't fit well with what science generally does, or with what physics usually says. And physics, especially in its early days, used to say that everything should be deterministic. Both Einstein and everyone else proceeded from the idea that if some process occurred, then the process must be strictly determined and must be strictly explained. But these views were revised, and it turned out that the observer effect is not seen as a choice among specific options, but rather as a case of absolute randomness. I've talked about absolute randomness many times before and have touched on this point repeatedly. And here, this absolute randomness intersects with the concept of hidden variables. That's what we're going to talk about today. In general, when I've discussed the observer effect in articles, videos, and many other places, I've conveyed the following idea, that there are a certain number of options we can choose from. And the very moment of this quantum choice, or the moment of detection, it selects that particular state, or no, selects is a bad word, that all sounds a bit mystical. Let's put it this way, it reveals the particular state the system is currently in. We have an infinite number of possible states the system can be in. And one of the options, the one that best corresponds to everything happening around, is determined through detection. Quantum views of reality are far from deterministic. And when I expressed this opinion, I was accused of promoting hidden variables. By hidden variables, as understood in physics, we mean the existence of certain hidden, essentially, yes, parameters, some hidden factors that can influence the system. And by the way, this logic seems incredibly sound. After all, imagine that we enter a dark room with a flashlight. We don't know what's in the dark room, we don't know what objects are there, we don't know what's scattered on the floor. And we assume that there is something specific in there. For example, we assume that there are books in there, but as we start to feel around for books, start to touch things, our flashlight only illuminates a single area or object, and everything else remains in darkness. We shine the flashlight at our feet so that, I don't know, we don't fall into a pit or step on a nail, and we start to feel around with our hand for something on the bookshelf. And it seems like we're feeling for books, but at some point our hand lands in a mousetrap. And that mousetrap was exactly the hidden parameter. The point is, we cannot speak of exhaustive knowledge about a system until it is fully formed. With quantum physics and quantum worlds in general, everything happened in much the same way. We cannot claim that we now fully or exhaustively, or even say 50% understand what is happening in this strange world that defies standard notions. We always see quantum physics as a kind of offshoot from classical physics, but this offshoot is so peculiar that everything there is the other way around. And under these circumstances, we can confidently state that we cannot fully describe this system, mathematically, physically, or in any other way. And at this point, there arises the temptation to say that the system behaves strangely under observation because these scenarios are described by these hidden parameters. If we reduce this logic to something more primitive, imagine that you know the speed of a car, but you don't know the parameters of its movement. You don't know what acceleration the car had. And you assume that the car was moving at a constant speed throughout the entire stretch of the road. Based on this, you expect it to arrive at its destination at a specific time. But in reality, there was another hidden factor, which was called acceleration, and the car was changing its speed during the journey. This change in speed prevents us from accurately calculating, so to speak, the car's arrival time, if we don't have the complete graph of the system's behavior at this stage, so to speak, of its existence. It's roughly the same with quantum systems, where there can be any hidden parameter that determines the strange behavior in the observer paradox. It is precisely the hidden parameter that can manifest as this detection effect. I want to note right away that the ideas I have expressed in my works regarding the observer effect are, in fact, not hidden parameters. After all, a hidden parameter is some property of the system or some factor that influences the system's behavior. But what I described back then implies something a bit different. The logic there was based on the idea that we have a certain number of existing probabilities, from which the most, let's say, suitable one is chosen. Yes, the system is probabilistic, but this probability changes depending on the existing context, on the way it is considered, and, well, let's say, on the environment in which it occurs. And according to this logic, my idea was based on the existence of an infinite number of probabilities, each with its own numerical characteristic. If there are many probabilities, then the one that fits best will be chosen from among them. And this is exactly what I was conveying in those materials of mine. But for some reason, people in the comments were very actively talking about hidden variables. And hidden variables, as you understand, are a bit different. Hidden variables are not probabilities, but factors. A quantum system is characterized by the fact that the logic we regularly use in our everyday lives does not apply there. The logic that works for us in classical physics and in general, everything we're used to seeing, doesn't work there. But when we talk about some kind of certainty, we once again step onto the path of determinism, the very path that is actively criticized, and it was precisely for this reason that some dissatisfaction was expressed in the comments on my work. The idea of hidden variables was criticized using the so-called Bell's inequality. This inequality is a purely mathematical approach that made it possible, in one way or another, to characterize the behavior of the system. Bell suggested that if you construct a mathematical system in the right way, then by taking certain factors into account, you arrive at an inequality. In this inequality, hidden variables are represented as a series of coefficients, and if the system is correct, you get one outcome. But if the system is incorrect, you get a different outcome. Everything started to revolve around this inequality, and here I want to immediately say, pay close attention to the approach. This is a purely mathematical description of reality. The hidden variables themselves are treated here as mathematical factors. Here perhaps one can agree with those who sometimes criticize so-called mathematical physics. The mathematical approach, unfortunately in my opinion, is not capable of accounting for all the constraints present in a system. And those very hidden variables may not be, let's say, a mathematical operator or a mathematical feature, but rather something real. So we end up with an interesting, amusing situation. It turns out that we've written an equation that is constructed from equations that already existed, and these equations confirm that such equations should not exist. That's exactly how it sounds. Bell essentially conducted a mathematical investigation, and this mathematical investigation may not correspond to real physics. On the other hand, even Bell's inequalities do not prove that there are absolutely no hidden variables. Hidden variables may exist, but perhaps not those variables that indicate the validity of local realism. There's a lot that can be said about the non-existence of hidden variables. A lot of references can be made to Bell's inequalities, and it can be argued that Bell's inequalities work as they are. All of that is fine. But who told you that Bell's inequalities are even derived correctly? And I don't want to criticize Bell. I don't have that level of qualification, nor do I possess such extensive knowledge to speak about the mathematical logic behind all these derivations. But I do have some common sense, or at least I hope so. And common sense suggests that you can't evaluate a system using the same approaches that already exist and are considered exhaustive, and then claim that there's nothing more in the system. It's like comparing, in that example about speed, the speed of a car and the time it was moving at that speed with the speed of the car when it was moving differently, and then saying that there's nothing else.